Hi, amazing students. I'm Teacher Ron. In the previous lesson, you learned about the characteristic of images formed by plane mirrors. And in this new lesson, we'll allow you to explore curved mirrors. And also, you are expected to determine the characteristic of images formed by curved mirrors. Are you ready, amazing students? Let's start.
So, what is reflection? Reflections in mirror are amazing things that tell us literally a great deal about how we see ourselves. But what do reflections tell us about the mirrors themselves? What exactly is a mirror and how does it work?
Rays of light bounce when they hit a surface. When the angle of incidence and the angle of reflection are equal, plane mirrors show regular or specular reflections. The angle of incidence and the angle of reflection are equal, according to the law of reflection. The normal line and the incident ray are used to measure the angle of the incidence, while the normal line and the reflected ray are used to measure the angle of reflection. Let's first clarify a few words before moving forward. So the reflected image that is produced can be described as follows. First, the images, either virtual or real. So the primary distinction between virtual and real images. They produce a real image when the rays converge, while a virtual image is formed when the rays diverge. So the second, orientation. If an image is upside down, it can be inverted. If it is right side up, it can be upright. So the third one is the location. The location of the object always determines the location of the image. So the last, fourth, the size. The size could be the same, larger, or smaller. Larger if the magnification exceeds 1, smaller if it is less than 1, and same if it is equal to 1. So the ratio of the image dimension to the object dimensions is known as magnification.
Did you ever try looking your image on both sides of your spoon? What have you noticed? This is an example of reflection on curved mirrors. A curved mirror is a portion of a spherical that reflects light. Curved mirrors come into two varieties, the concave and the convex. An example of a curved mirror having concave and convex sides is a spoon. The main difference between a concave and convex mirror is the way they reflect light. A concave mirror reflects light inwards, while a convex mirror reflects light outwards. This difference is due to the shape of the mirror.
Concave mirror. The principal axis of a concave mirror is a line that passes through its exact center. The letter C represents the center of curvature, which is the point in the middle of the sphere from which the mirror was cut. The letter P stands for the vertex, which is the location on the mirror surface where the principal axis and the mirror meet. The geometric center of the mirror is called the vertex. So the focal point is represented by the letter F. It's located halfway between the vertex and the center of curvature. The characteristics of the images are unaffected by the object's location in convex mirrors. Convex mirrors always create a smaller, upright, and virtual image on the other side of the mirror. So the characteristics of the images created by convex mirror are easily predictable because in a contrast to concave mirror, convex mirror always produce images that share this characteristic. Both convex and plane mirrors only create a virtual image. Only when the object is positioned farther away from the mirror surface than the focal length can a true image be seen in a concave mirror. In other words, a virtual and magnified image is created when the concave mirror is positioned very close to the object. As the distance between the object and the mirror increases, the image size decreases and the actual image are created. Both concave and convex mirrors are subject to the same law of reflections as plane mirrors. Rays of light converge at a point known as the focus when they reflect off a concave mirror. The distance between the focus and the reflective surface is known as the focal length. Concave mirrors create an image that is smaller and more realistic. Conversely, convex mirrors produce an image that is larger than the virtual object. And now, let us determine the characteristics of the images formed by the curved mirrors. Using the mirror equation, which is the 1 over f is equals to 1 over p plus 1 over q, where the f is the focal length or the distance from the mirror and the focal point. P is the distance of the object from the mirror, and the letter Q is the distance of the image from the mirror. We also use the magnification equation, which is the Q apostrophe over the H is equals to negative Q over P. Now, keep in mind that the focal length is negative for a convex mirror and positive for a concave mirror. If the image is real and in front of the mirror, its distance is positive. If it is virtual and behind the mirror, its distance is negative. The image height denoted by H apostrophe is positive when it is upright and negative when it is inverted. Let's try some sample problem. A concave mirror with a 10.5 cm focal length is positioned 45 cm away from a 5 cm tall light bulb. Calculate the image size and distance. So we are going to identify first the given. So we have here the height of the object, which is 5 cm, distance of the object, which is 45 cm, and the focal length, which is 10.5 cm. So we are going to find the distance and the height of the image. So we have here the formula. 1 over f is equals to 1 over p plus 1 over q. Next, we are going to replace the focal point, the distance, and the height of the object. So we have here now the 1 over 10.5 cm is equals to 1 over 45 cm plus 1 over q. Next, we are going to subtract both sides by 1 over 45 cm, so this is the result. So after subtracting both sides, we have here now the 1 over 10.5 cm minus 1 over 45 cm is equals to 1 over q. Now we are going to multiply to our denominator to the other side. We have here down a 45 over 472.5 cm minus 10.5 over 472.5 cm is equal to 1 over q. Next, we are going to use the cross multiplication. And here's the result. After that, let's divide both sides by 34.5. And for the last step, let's divide the 472.5 cm over 34.5. And this is the answer. Q is equals to 13.7 cm. For magnification, we have the formula of H apostrophe over H is equals to negative Q over P. Let's replace the value of H, Q, and P. So we have here now the H over 5 cm is equals to negative 13.7 cm over 45 cm. Next, we need to use cross multiplication. So we have here now. Next, let's divide both sides by 45 cm. And last, divide the negative 68.5 cm squared over 45 cm. And this is the answer. So we have here now the H apostrophe is equals to negative 1.5 cm.
Oh hey, what are you doing? Oh, this one? This is what we call ray diagramming. I am trying to locate the images formed in a convex mirror. So take a look at this figure. What have you observed? There are arrows that are moving towards the curved mirror and is reflected. Exactly. There are rays of light coming from the object towards the mirror and is reflected at different points. And as you can see, there is an intersection between the two rays, and this is where the image is located. This is the representation of ray diagram. In doing ray diagramming, we have to consider four major points. The center of curvature, in which it is where the mirror or sphere is being parted, the focal point where rays tend to diverge or converge, the vertex, in which it is the middle part of the mirror, and lastly, the principal axis. Now, from these points, we can now move to how these points are important to ray diagramming. We have what we call the P to F ray, F to P ray, C to C ray, and lastly, the V ray. For a concave mirror, P to F ray is where a ray of light from the object is parallel to the principal axis and will be reflected towards the focal point. Meanwhile, in a convex mirror, a ray of light from the object is parallel to the principal axis and is reflected as if passing through the focal point. Next is the F to P ray. In a concave mirror, the ray of light from the object will pass through the focal point, and when it reaches the reflective surface of the curved mirror, it will be reflected parallel to the principal axis. On the other hand, in a convex mirror, the ray of light will move towards the focal point behind the mirror and reflects parallel to the principal axis. The last two are the easiest to remember and do. The C to C ray for both convex and concave mirror, where the ray of light from the object will pass through the center of curvature and be reflected back again towards its own path. And lastly, the V ray or the vertex, again, the ray of light for both convex and concave mirror will move towards the mirror and be reflected at an equal angle. Now, let's put it into use. A 150 cm tall woman is placed 250 cm in front of a convex mirror with a focal point of 100 cm. What is the image location, orientation, size, and type? First is the P to F ray, where the ray of light from the object will move parallel to the principal axis and is reflected towards the focal point. Followed by the F to P ray, where the ray of light from the object will move as if passing through the focal point and is reflected parallel to the principal axis. We also have the V ray, where the ray of light from the object will move towards the mirror and is reflected at an equal angle. From here, we can now see that there is an intersection from this ray in this point. This is where the image will be located. Now, from this ray diagramming, what do you think is the location of the image? Exactly, before the focal point. How about the orientation? We have two types of orientation, the upright and inverted, and this image is an upright image. Next is the size. Is it the same size of the object or not? Very well said. It is a reduced or diminished size since the image appears smaller than the object. And lastly, the type, which is virtual image.